So, good morning. I am Krishna Kumar. Welcome to the classroom. Yeah. So, we have been looking at the initial value problem. We have already proved using the Cauchy-Euler approximation that there exists a solution on locally, and even said something about that there exists a global solution in the sense that there is a maximal interval on which the solution exists. Now this has been done, and we have also said in the last few theorems that we have looked at, it analyzes what happens near the boundary or how the solution behaves at the end point or in the neighborhood of the end point. Now we introduce a new approximation method, more popularly known and often more popularly taught also, the so-called Picard's approximation. Method. This is different from the approximation method that we have introduced earlier, that is the Cauchy-Euler approximation method. Now both has its own merit and advantages. Now you see that the idea is the following. So I have put down the initial value problem on the top. Now what we have is the following. So the equation that you have to solve is y dash equal to f of xy, and we have assumed that we have got the h interval as given. So what we did was we constructed the rectangle R defined as the set of all xy such that mod x minus x naught less than or equal to h and mod y minus y naught where m, of course, what we did was we considered the whole problem on a bigger interval mod x minus x naught less than or equal to a, mod y minus y naught less than or equal to b. This is where we started, such that this is contained in B. Then of course you know that this is a compact interval, compact subset of R2, and f is continuous, therefore f is bounded. So M is the bound of f on R. On the rectangle R. Yes. Then what we did was we defined h as the minimum of A and B by F. So with that we constructed R, and you know that R actually contained in this, right? So let me draw the rectangle R. This is x naught y naught, which is the initial data, and then this is h, this is mh. So we constructed R. Now what you have is the following. We are going to prove that there exists a unique solution of the initial value problem on the interval x0 minus h to x0 plus h, provided f satisfies the Lipschitz condition. So let me assume f is Lipschitz. Constant k. This is the assumption that we make, right? So if these conditions are satisfied, there is a unique solution on this interval h that we have on the interval of length 2h centered around the point x0. So this is the theorem that we prove. So let us look at the following problem. See, suppose there is a solution. Satisfies this differential equation. Then what do you get? You have phi dash x equal to f of x what we have is that phi is an admissible function, and admissible function in the sense that whenever x belongs to the interval x0 minus h to x0 plus h, you have x phi x in D, so that f is defined, or more specifically x phi x is in R. So this is well defined, and what you have is this, that phi is a differentiable function and the derivative is equal to the value of the function at y is equal to phi x for all x belong to this interval. Now this is what you mean by a solution. Now one thing that you can do is here convert this differential equation into an integral equation. Okay. Suppose there is a solution, then what you have, this is what you have. Therefore, I can write, suppose x belongs to x0 plus h, x0 then you see that integral x0 to x phi derivative, I introduce the dummy variable to differentiate it, to integrate it. This is equal to integral x0 to x f t dt. If this is phi is a solution, then this is true, and therefore this is true for x belonging to this interval. Therefore, let us integrate this. Now this can be easily integrated. So this is going to be phi x minus phi x0 that is, we have phi x minus y naught equal to, or phi x equal to, phi x naught is y naught look at this. This is an integral equation. Have we solved the problem? We have not. What we have done is only converted the initial value problem into a differential equation. Sorry, an integral equation. Therefore, what we observe is that any solution of this problem is a solution of this integral equation. Okay. Therefore, and is the converse true? If the converse is also true, then you see that this integral equation is equivalent to the initial value problem that you have started with. So we will work on that. So let us see that suppose, okay, what is the integral equation? The integral equation is this: y equal to so this is the integral equation that we have. So you are saying that phi y is equal to phi x is a solution of this integral equation. Conversely, suppose y is equal to phi x satisfies the integral equation. Then what you have? Y is a continuous function, and if it is admissible, I mean these are the conditions. If it is admissible, then you see that this is well defined and all this integral is well defined, and what you have is that y becomes not only continuous but it's also differentiable, that the derivative exists everywhere on the interval mod x minus x naught less than or equal to h. In that case, what happens? We can differentiate this. If you differentiate this, what you get? Dy by dx equal to, this is a constant, therefore you have the derivative of this, so that gives okay. So y is now a solution of the initial value, sorry, the differential equation that we started with, and you can check that y x naught is equal to y naught. Therefore, any solution of this initial value problem is a solution of the integral equation, and any solution of the integral equation is a solution of the initial value problem. Therefore, the two problems are equivalent. Now, this is the whole idea behind the Picard's method, this observation. So, what have we done? We have converted the initial value problem into an integral equation. Now, see, we have not solved it yet, but we will find out some mode of solving it. Okay. One observation that you make is this: suppose you start with some function which is admissible. Okay. So let us start with a y equal to, we take phi naught is admissible. If it is admissible, it is in the domain of, that is t phi t, t phi naught t belongs to R. Okay. If so, f is meaningfully defined and this integral makes sense with y replaced by phi naught. Now we will just define so we construct a new function phi 1, okay, starting from phi naught. Now one choice for phi naught that is usually taken is phi naught x is taken identically equal to the constant function y naught. That works. So you can go ahead to construct phi 1. Having constructed, you can go to construct phi 2 and so on. And suppose you have constructed phi n, then you can construct phi n plus 1 so you continue the process. Okay. From every phi n you can construct a phi n plus 1 provided phi n is admissible. That's all the requirement. So the question that you ask is this: is phi 1 admissible? First of all, suppose if phi n is admissible, is phi n plus 1 admissible? So the only requirement that you need is that these functions that you generate starting from an admissible function gives rise only admissible functions, so that always ft phi kt or phi nt is defined. So you can go to the next one. Okay. Therefore, what you get? You would construct a sequence of functions phi nx which are continuous and solutions, okay, and also differentiable. I mean, that comes from the fact that you are constructing it through an integral equation. Okay. Therefore, formally, if you take this and then let n tend to infinity, this is what you have. And you see that as n tends to infinity, suppose this converges, whatever some norm on the interval x0 minus h to x0 plus h, or you have a function space, etc. We will formally do all that. And suppose phi nx converges to some phi x in some sense. These are all formal statements. phi x. Then what happens? Limit n tends to infinity, phi n plus 1x is also phi x. Therefore, if you proceed to the limit, see, all this has to be rigorously worked out. So you end up with phi x equal to y naught plus limit n tending to infinity of this integral. We assume that limit can go inside and use the continuity of f, etc. So you eventually get the limit can go inside the function f also. So you get this is equal to integral what does it mean? It means phi satisfies the integral equation. Okay, phi satisfies the integral equation. Essentially what has happened, now let us analyze this. See, we have a machine. What is this machine? Machine is this. Let me draw a machine. There is an input and an output. And there is some activity happening inside. And this is described by the following: y naught plus so the activities are, suppose you put y inside here, some y, some function phi over there. What happens? It first goes inside and then a function of t is computed and then you integrate over this. So you get a function of x, add that to y naught. Now this is the operation, this is your machine, this is what the machine does. So when you put the raw material here, say something like phi x, what comes out is y naught plus integral x naught to x f dt. So in particular what you are doing, you have start with phi naught, then what you have, this is the one that you have, which you have designated as phi 1. So if you put in phi naught, you get phi 1. If you put in phi 1 back again, you will get phi 2 and so on. So successively you keep, generating a sequence of functions, provided the functions that you generate at each stage is an acceptable function as a raw material for your machine. Okay. What are the conditions that it is a raw material for the machine? This integral should exist. Okay, that is the primary thing. So f should be, so f t yt should be a admissible function, so that this makes sense, and then you can add it to y naught and you get this. So this is the machine that you have, right? And so you get this is also sometimes called a bootstrapping. You put the lace in and then again back to the same place and then put it back and so on. Okay, so it is successively you put it inside the machine and extract it out. And eventually what happens is that started with a function y naught and it undergoes several iterations of this kind. And eventually this will go to a rather smooth function, so that when you put that function there, ultimately the same function will come out unscathed. Now this is the property of the limiting function that you expect. So this is the idea of what you have. So therefore, it is pretty clear what you have to do. What are the things to be done? First of all, we prove that if you start with an admissible function and send through this machine, you get an admissible function. That is something to be verified. The second crucial thing that you have to verify is that you get a sequence of functions. Now every function is an admissible function. You have to show that this sequence of functions converge to a limiting function. Okay, so that limiting function also should be naturally a function which is which is admissible. Therefore, it can go inside this and work and generate another admissible function. And then you show that essentially, if you take the limit can go inside, limit can interchange with the integration and go inside, and then it can enter the function f, and the limit can be exercised there, and eventually you get phi n. So you get a sequence of functions phi n converges to phi in some sense. In that sense, we will make it clear. So this is the whole idea of Picard's approximation. In my next part of this lecture, I will be dealing with the generalization of this idea, and that will lead to the so-called contraction mapping principle. So let us start proving every one of these steps. Okay. So it is clear to you now what to be done. So each one of these tasks we undertake and then put them together, you will get the result. You will prove that phi is a solution of the integral equation, and since it then equivalently it is a solution of the initial value problem. So the first lemma is suppose y x for x belonging to some interval x1 x2 is admissible over admissible. That is, the meaning of this is that x, y, yx belongs to D, then I will take it as, it could be even an endpoint, doesn't matter, but we will take it as. Then a necessary and sufficient condition a necessary and sufficient condition that y is a solution of initial value problem or rather the differential equation. Is that it satisfies, it is the solution of the integral equation for some constant y naught. Okay. Now what happens is that this solution has the property that so that is quite easy to prove. We have proved it. We have assumed that yx is a solution. Then you see that if it satisfies this, then you show that it's a solution of this integral equation, because you can derive this integral equation from the initial value problem. Conversely, suppose you have the y as a solution of this integral equation, then you immediately observe that yx naught is equal to y naught, and y is differentiable and y derivative is equal to fx by x. Therefore, the remark equivalent to integral equation, i.e. integral equation okay. So that's the remark. So instead of working on the initial value problem, you can work on the integral equation. Okay, so that's our next task. Now we have the following lemma. So now these are we are slowly working on the various results that are needed to substantiate your operations. Solution, suppose you take R to be as defined there, that is x, y, you see that M is the bound for F on S, and then from there you construct this H. H is the minimum of and A and B are from the definition of S. Okay. let phi naught be an admissible function for the two, right? Let phi be an admissible function with continuous first derivative on mod x minus x naught. Okay. So define let just understand the result. We start with a admissible function and then plug it inside the integral equation, then you end up generating another admissible function satisfying certain conditions of differentiability, etc. So that you can proceed further, so that your raw material gets ready for your machine. That's the meaning of that. Okay, so let us write down that. Okay, let's prove this. So what do you need for this? So the question that you ask is this: is if it is in R, it is in D. Now we prove that this is in R. For let us compute this. So what you have? This is what you have. So you have see how is psi defined? Psi of x equal to dt. Therefore, you have psi x minus y naught therefore put a bar here because I don't know whether x is greater than x naught or x is less than x naught. That is not okay. Now you see that phi is admissible. Okay. Therefore, you see that less than or equal to m. So which implies so if whenever mod x minus The other two parts of the statements are very simple to verify. This is differentiable, that is because you see this is a continuous function, you are integrating over the interval this, and then this is a constant function. So you get a function which is differentiable, whose derivative is also continuous, and that is the therefore psi is admissible. Now this is going to be a crucial thing in the argument, because we start with an admissible function, put to the machine, you get another admissible function, put it back, you get another admissible function. Therefore you generate a sequence of admissible functions. Okay, so that's our technique. So this is what you have. You have so this is ultimately the recurrence formula that you have, which generates the sequence of functions y. Now what next? Want to prove that the sequence converges and becomes a solution of the integral equation, and therefore it's a solution of the differential equation. So as I said, there are a few things to be verified that will give you the result. Okay. So let me write down the theorem. Essential features of the theorem. Now we assume F is Lipschitz. With constant. This we shall use at some stage of the theorem. D or in R? R is enough. Right now we are only interested in local solutions. Then what you prove is this. The sequence phi n converges uniformly that is one statement. Uniformly and absolutely. To a function phi of x satisfying the integral equation and for mod x minus x naught, and hence the ideal. So let us start working out the various steps. So let us assume n be the, or some number n, error satisfies the equation one, that is the IVP. IVP on therefore what does it mean? It means that is less than or equal to okay for mod for instance, suppose you were to take phi naught as phi naught, then you see that it automatically satisfies the initial condition. It is also admissible. Therefore, d phi naught by dx is 0. Therefore, this is absolute value of this, and this is bounded by m. So, m becomes that particular number n in that case. For if phi naught is taken as equal to y naught, then mn is equal to. Now, integrating this, so what you have, so let us look at what happens with phi 1. So, we will estimate this. What is this? This is equal to this is this, because this part gives you phi 1. Okay. Therefore, you see that this is equal to this is equal to this, because if you integrate this you get phi naught x minus phi naught at x naught, that is y naught, and then this is what you get. Now we can estimate this. If you estimate this, this is what you get, integral x naught to x this is less than or equal to n times mod x. Okay, so that's quite easy. So this is one estimate that you have. Now what you do is you recursively calculate this. We will work out the estimate for the entire phi n. So what you have, claim that is the Lipschitz constant n mod x minus x naught this of course we prove by using the induction, process of induction. Induction for n greater than or equal to 1 and mod c x greater than or equal to x. You can likewise prove it for x naught also. So it is the same sort of proof that you can advance. Assume okay, first we observe that this is true. Assume n equal to 1, n equal to m. Then we show that that's the argument that you have. So let us compute this. So you see that phi m plus 1 let us estimate this. Now this is less than or equal to integral x naught to x. Now I can write here integral x naught to x because I am assuming x greater than or equal to x naught. Otherwise I have to put a bar there. Okay. Now by Lipschitz condition, then what you have is that phi is less than or equal to k times dt. Okay, now estimating. So for n equal to m, what we have is this. This is the assumption that we are making for n equal to m. Since x is greater than 1, this is essentially t minus x naught. Okay. Otherwise, there will be a minus sign. Okay. Then this we estimate k to the power m n into mod x minus x naught therefore that concludes the proof of the induction part. So you are assured that there is a sequence of functions with the desired properties. Okay. So that implies there exists a sequence that means you have a series see look at this one. Look at this series. Now if you take the partial sum, say n to say some m, n equal to 1 to m, then you will get FIM. Okay. So if you take this series from n to m, okay, therefore you see that, so what we prove that the series is uniformly and absolutely convergent. Okay. Now, for that, all that you need to do is, now we have the estimates here. Just put in that estimate. Okay. And so you give the proof. You have the estimate for each of these terms in terms of that inequality, and then you have you show that this absolutely convergent on less than or equal to h, assuming x positive, I mean x greater than x naught. Likewise, you can give a proof for x less than x naught. Therefore, we take it that this is proved on this interval. That is quite easy to see, because you look at this series and then mod x minus x naught is less than or equal to h. So you can show that this series converges. And that's very easy, because of the m plus 1 factorial sitting in the denominator. Everything works beautifully. So this is uniform convergence of phi n. To phi x. What can you say about this function phi x? This phi x is a continuous function. Okay. Right? Then phi x is, phi is continuous. And you can show that it satisfies the integral equation. What is phi x? Phi x is equal to limit n tending to infinity of which is equal to, because it's a constant, plus the limiting operation comes here, therefore you will get limit n what is it? Yeah, n tending to infinity of integral x naught to x f t. Now we have used the arguments earlier that once the sequence converges uniformly, you can interchange the integral and the limit, because it's a bounded interval anyway. Okay, so the limiting operation goes inside, and then because of the continuity, simultaneous continuity of f in both the variables, it can go inside, and then you can let n tend to infinity. Therefore, you are eventually getting the relation that this is equal to so uniform continuity and the fact that this is a bounded interval, everything goes to. So there is no problem. So it satisfies the integral equation. Therefore, it satisfies the integral equation. What does this mean? Initial value for that's the result. Now you can give a quick estimate of the error. So this is the error that you compute, and you can show that this is actually less than or equal to infinity. So you can use this kind of formula for that, and then you get estimate this is less than or equal to n by kh to the power r by r factorial, and this is less than or equal to check whether these numbers are ready, or there may be some error in the summation or something like that, but that you do it. So this is equal to n by k e to the power into this is the error that you can estimate when you replace this solution by phi. So what you normally do is start with some phi naught, compute the first few terms, and then you see that if h is sufficiently small, that means you are in a small neighborhood of the point x naught, then you get a good reasonable estimate for phi in terms of the n. You may not have to take n too large to get that, okay, right, because this number is quite powerful. Okay, thank you very much. I stop here, and now I will return to my I'll continue with this lecture, and to give you some of the very wonderful ramifications of this, and I'll join the discussion towards the end. Okay, Thank you very much. So we will meet around say around 12 o'clock. Yeah, right. Thank you very much.